So back to the problem that we had. So what was the idea? We saw the Langevin dynamics. So it's telling us that if you put the score function in the drift term, then essentially the thing that is going to happen is that through time, you're going to converge to one sample which is looking like the distribution that you want, right? And this brings up the idea of a score function, score models. And the idea of a score model is that, well, I can just assume that that score function that I don't know, right, is a neural network. And then I can put that neural network, I use my data set to train this neural network, such that this model is somehow mimicking or approximating the score function of my data, right? Once I have that score function, then I'm going to put it inside the Langevin dynamics, and it's going to sample from the distribution for me, right? So the whole idea is to just learn the score function instead of learning the distribution itself, right? So it's still a bit explicit in the sense that I'm learning really the score function, not giving up everything and only sample. But still, I'm not learning the distribution itself, right? I'm learning a score function. But we're going to get rid of this score as well soon, okay? Now, what is a score model? What can be the score model? So score is the gradient of logarithm of px, right? So if your x is d-dimensional, what is the dimension of your score function? It's going to be again d, right? Because it's the gradient. Gradient means that you have the derivative with respect to every single entry, right? So the gradient is if of the same size of x, right? So this is score function, this is score model, should be a neural network which takes a d-dimensional input and returns a d-dimensional output, right? Everybody's cool? So d-dimensional input goes in, d-dimensional output comes out. And you can put any computational model, and what you hope, you hope that this model, you can come up with a kind of a strategy that this model can somehow approximate the score function of your data, right? Which is this guy, right? The gradient of logarithm of your data distribution. Do you have the score function of your data, the truest score function? Do you have it? No, right? We don't know the distribution. We don't know that score function as well. We want to only approximate it. Now, there are two key points about this score function. One of them is that this score function is pretty much like the energy model or flow model. They don't need to have any specific property, right? A distribution needs to add up to 1. It should be always positive, correct? But score function doesn't need that, right? So it could be any model. In terms of defining a model, it's going to be much easier for us, right? So this is one point that it has. The other point is that if we have a score function, we don't have any problem with sampling anymore, right? So back to days when we started with just learning the model, the distribution, we said if we have the distribution, now we need to figure out a way to sample, right? This was why we just thought about a specific modeling, autoregressive modeling, because we could just sample conditionally, right? Or energy-based models were really trouble. We had to come up with sampling algorithms. But here, really, we don't have any issue. Actually, once we have the score function, we just put it in the Langevin dynamics, right? And this is going to do the sampling for us. So sampling is not anymore an issue as we had it in a general distribution learning, right? So these are the benefits that we can get, and you can guess this because essentially we are learning something at least, say, informative as compared to the distribution itself, right? You can get from distribution to a score, but you cannot get directly from a score back to distribution, right? It's hard to get back, and this is the main reason. Now, the point is that, okay, you might ask me, let's say that we put one neural network, so it has d-dimensional input, d outputs, perfect. Now, how we can train it, right? How can I come up with the idea with finding the right choice of W, right? Now, if you want to train it, what do you need? A general machine learning question. So assume you are in a job interview. You want to train a neural network. What do you do? You need gradient, right? For gradient, you need a loss function, right? And a loss function that you can compute, right? So everything inside the loss function is possible to be inserted, right? So basically, we need to just have one loss function to minimize and eventually compute the gradient. And that loss function is this guy. This is what we call it score matching, right? The score risk, and then if we minimize it, this is a score matching. What is the idea of a score matching? It says that you get the neural network, your score model SW, and then you compute this difference with the true score function. You take it to power 2, so you compute the norm. This is eventually telling you how different your score model is from the true score function. And then the expectation of this guy is what we call it the score risk. Okay? And once you minimize it, this is going to be score matching. Everybody's clear? Now, can you do it? Can you do a score matching?
Don't we need the score still?
Yeah, this is the point, right? So the point is that we also need a score here, right? But do you think there is a way that we get rid of this score? There must be, right? So you remember when we wanted to train distribution, right? We said we have the data distribution. This is our model. We want to minimize the KL divergence, right? And then if we wanted to compute the KL divergence, we needed to know the data distribution, right? But then when you write it down at the end of the day, you see the only thing that you need to minimize is essentially minus log likelihood, right? And that one doesn't need the data distribution to be estimated, right? So you said, okay, I can't do it by my data set, correct? So if you see it like this, you don't need to panic right away, right? Lots of people panicked and they didn't do it. Hayfegenin, he didn't panic and he just ended up with the result, the famous result he developed on this. Okay? So we have this guy. The point here is that that S is written in terms of the distribution. We don't have it, that's right. But maybe when we expand this, we're going to see at the end of the day the function which we want to minimize in terms of W, in terms of the model parameters, is not really needing to have that data distribution explicitly. Everybody's clear what I'm trying to do? So I want to see whether I can write this term down in a way that I get rid of that S explicitly inside the expression, right? And if I can do it, then I'm going to approximate it by sampling. Okay, so let's start doing this together. This is the messy part, and after that, everything going to be easy, okay? I promise, like my previous promises. Okay, yeah. So let's say that I want to compute this expectation, right? This is the model that I have. This S, this guy, is the one which is problematic. I don't have it, right? But let me expand this guy. How can I expand this one? Norm of the difference of two vectors is going to be norm of the first vector plus norm of the second vector minus 2 times the inner product, right? So I'm going to do that. I'm going to write it down. Norm of the first vector, norm of SW. Norm of the second vector, norm of S. Norm the minus 2, inner product of my model, and S, right? Everybody's clear? Now, the blue term here, I cannot compute it. I do know that. But do I need to compute it? There is no W there, right? If I want to minimize this guy, I don't need this one, right? Okay, that's exactly what happened when we were doing the maximum, the KL divergence minimization. So we want to minimize with respect to model. This means that we want to minimize with respect to W. This blue term does not contain W. So essentially, if I want to minimize this guy, I need to minimize this first term and the last term, right? And the blue term, I can just throw it away. Everybody's cool? So in these terms that I want to compute, can I compute the first term? I can compute, right? This is the output of my model, right? So I look at the output of the model, I compute the norm, and then I want one expectation, so I can do estimate it by sampling, right? So that is OK. I can estimate this guy by sampling. What about the second term? Can I do it? No. I need the score function itself. I don't have it, so still that guy is problematic, right? But it's still one step forward, right? We got rid of that blue term. OK. Let's go one step further. Let's write down the definition of this inner product, right? This expectation. If I want to take this expectation, I'm going to take the integral of this guy multiplied by px and then dx, right? This is the definition of expectation. Everybody's clear? Now, next thing that I'm going to do, I'm going to replace this score function with this definition. So I'm going to have the gradient of logarithm of p times p dx, right? So s is just replaced by its definition. Everybody's cool? S is gradient of log of p, right? Now, gradient of log times the function itself. What is this guy? We did it today. Again, gradient of log of px is gradient of px divided by px itself, right? So this guy comes here. Now, px times gradient is gradient of px, right? So this guy is essentially px, right? And I can write down this integral in this form, right? Easy. Everybody's clear? Question? So now what I want to compute, I need to compute this one, right? And now, since this is an inner product, let me just expand this guy, right? So the inner product, it means that every single corresponding pair of corresponding terms are getting multiplied, and then I sum them up, right? So I'm going to open it up. So entry I multiplied by the entry I of the gradient, right? What is the gradient? The gradient of p of x, this is going to be partial derivative of p with respect to x1 till partial derivative of p with respect to xd, right? So I am going to get this one, multiply with the first entry of my model output, and then second one, second model output, and so on. Once I added up everything, then I'm going to take the integral with respect to x, right? Everybody's cool? Questions? Now, this summation, I can take it out, right? So I can take the summation out. This can be like the integral of this term dx, then I take the summation, right? This is still the same thing, right? Okay. So now the main task that I want to do is this one. I want to compute the integral of one function multiplied by the derivative of one function dx, right? Okay. Let me write it down easier on the board so we see it together. So I want to compute the integral of s of x. Right now, I just dropped all of those w and I. I just want to simplify everything. Now I have the derivative of p with respect to x dx, right? Now, I would have been happy if instead of the derivative of p, I had p itself, right? Everybody agrees with me? If instead of the derivative of p, I have p itself, I am super happy, right? Because its integral of something times p dx is expectation, right? An expectation, I can estimate it by samples that I have, right? So the issue is that this guy is not p, it's the derivative of p. Do you know of any trick in calculus that can convert this integral into something in terms of p? Great. Integration by part, right? If you do integration by part, then you can just change instead, you can replace this guy with p, right? Because you are not working with the derivative of this one anymore. You're going to have the derivative of this guy and the multiplication of the two, right? And in both of them, you're going to deal with p. So everybody knows integration by part, right? Anyone here doesn't know that or forgot? Do you want me to explain how you can do integration by part? It's no shame to ask. You know that? Do you want me? Yeah, so no worries. I mean, you want to compute this integral, right? The integral of f times derivative of g, right? You want to compute this one. So this is integral. Maybe I do it on the board first. So you want to do it to the integral of f of x, g prime of x, dx. Okay, you want to take this integral. Now, one thing that you can say is that if I write f of x times g of x, and I compute the derivative of this one, what is this derivative? F prime x times gx plus f of x times g prime x, right? So this is the definition of this derivative. Okay, now I have this guy in the integrand, right? F times g prime, right? So one thing that I can do, I can take this to the other side, right? So this is going to be minus equal, right? Clear? So I can write this guy down as integral of f of x gx dx minus integral of f prime x gx dx, right? Yeah? Now, integral of, sorry, here is a prime. Integral of derivative of something dx is the guy itself, right? So if I'm taking the integral from a to b, then I can just remove this one, also remove this one, and compute this at a, first at b minus at a, right? Yeah, okay, no worries. Correct? And this one, I take the integral from a to b, right? Now, if you look at this one, here I have g, here I have g. I don't have any g prime anymore, right? So this is what we call integration by parts. So if you want to compute this integral, so you can use exactly the one which I wrote on the board, this fact, and then you're going to end up with this conclusion, that the integral of f derivative of g is going to be fg minus integral of the derivative of f times g, right? So same thing we want to do here. What we want to do, we have s times derivative of p, right? And I want to do integration by part. Can you tell me how does it look like? It's going to be s is the function, right? The other function is p, right? So you get s times p, integral from a to b, right? So this is going to be s times p from minus infinity to plus infinity. I have done a bit of simplification here, you can guess, because I didn't take, I mean, this is not a correct one. I need to first take the integral of everything inside x. Only xi remains, and then you're going to have xi here, right? But forget about it right now, okay? It's not important. So s times p minus the integral of the other guy, right? So derivative of s, si with respect to xi times p dx. Everybody's cool? So this is just integration by part. Everybody sees that? Questions? No question? So what is the first term shown in red? It's 0, right? Because the distribution at plus infinity and minus infinity, again, if it's a nice distribution, it's the right distribution, this is going to be 0, right? It's never keep up, right? So that term is 0. The other term, what is it? I don't mean what is it explicitly. What kind of operation is that? It's expectation, right? Because it's integral of something times px dx, right? So it's expectation. So what you can say this guy is 0. This guy is expectation with respect to p of this particular term, right? The derivative of your ith output of the score model, right? Questions? No question? Okay. If you got no question, now we wanted to compute this one, right? The inner product between our model and the true score function. Then it turned out to be this particular summation, right? Summation of all of these integrals. And every single of these integrals, I can write it down in form of this expectation, right? So I can take that expectation, put it here, right? So it's going to be minus this expectation. I'm going to replace it here. This is summation over I. This is expectation. They can exchange, so I can take back the summation inside. So this is going to be expectation on the data distribution of this term. Okay? Everybody's clear? Questions? No question? No? Now, one thing, because I have the feeling like you find it too much. Let's think about the kind of integral, the kind of derivative we're computing here, this guy, okay? Let's see if I have this. Say I have the score model. This guy is SW, okay? Now, as the input, you're going to have x, right? What is the dimension? It's going to be x1 till xd, right? What would be the output? Again, d, right? So we said the score model is going to take the d inputs and going to convert it to d outputs, right? So it's going to be SW1, so I'm going to show it by S1 of x till d of x, right? Now, what are the terms that you are computing here? You're looking at this guy. This is the first output. What do you need to compute to put it here? Its derivative with respect to x1, right? So this is the first output. You're going to take the derivative of s1x with respect to x1, right? So you keep on going like this, right? So this is going to be, again, the derivative of sd with respect to xd, right? Everybody's cool? So you got what we are computing here? And now once you have computed all of these guys, now you add them up, right? You add all of them up. So these guys are going to get added all together, right? And this is going to be this particular term, right? So this term is a bit of like messy in face, so we don't like it. So we're going to call it what we call it score divergence, okay? So this is what we call it score divergence. This is divergence of our model SWX, right? So this is what we call it score divergence. So score divergence is essentially that particular term that you have inside the expectation. This is not a kind of, it doesn't reduce to something simple, right? This is what we call a divergence. But the important thing about it is that we can compute it, right? So if I look at this output, I need to compute the derivative. And once I have the derivative, I add them up. This is going to be the divergence. Question? No question? Okay, so this is the divergence. This means that that particular expectation of the cross product that we had is going to be minus the expectation of the divergence. And now we're going to have a nice final expression for that we can compute, right? So if we get back to the term that we wanted to minimize this guy and the minus 2 times cross term plus the blue term. We throw away blue term because that does not depend on W. Now that cross term is again written in this form, right? The expectation of the divergence. And looking at these two expectations, can you now estimate them given the data set that you have? Yes, right? Because the first one, you just get the output of your model. You need to take the expectation with respect to P. So you're going to just average over the data set that you have, right? The other one is the divergence. This guy, again, you can compute it for every single sample that you have. You average it over the data set. This is, again, going to be an estimate of this expectation. So this guy, we can estimate, whereas the original score matching risk, we couldn't, right? Everybody's cool? Right? So this is the same thing exactly with a bit of more calculus as we did with the KL divergence, right? We wanted to just minimize the KL divergence. We wrote things down. At the end of the day, we remain with one expectation, which we could estimate, right? Here is, again, the same thing. Questions? So this was a result Apo Hyferinen just developed. He is a quite well-known Finnish computer scientist. And he did it in 2005, I guess. And at that point of time, people were like, who wants to do a score? But yeah, it turned out that the diffusion models are something right nowadays, right? So nobody at that point of time expected this to just be so sophisticated result, but this is very, very important result. Okay? Question? So moral of the story, if you want to do, you can use Langevin process to just sample using simply a score function. And if you want to just train one score model, you can essentially minimize this particular loss function, which we are calling score risk. So if you want to just compute it in practice, you are going to just take samples from your data set, and then instead of those expectations, you are going to estimate it by averaging over those samples, right? Any questions? Was it too hard? It was?
So basically the second term is we are calculating covariance between SWX and SX. Like it's like
this one, you are computing the correlation, not the covariance, not the alpha product. It's the correlation, right? Right. You are computing the correlation.
Correlation is we only need to care about the sum of the elements in the main diagonal of the Jacobian matrix.
Yes, exactly. So this guy, you can actually write it down in terms of the Jacobian, exactly. So if you have the output, you can compute the Jacobian, but you have lots of terms which you don't need. You only need the main diagonal. That's right. Yeah. So if you get the Jacobian of the score with respect to the argument, right? Not with respect to the parameters. This is important. You're not taking any derivative yet with respect to W, right? This is only with respect to X, right? And then, yes, you take the trace. This is going to be your divergence. This is called divergence because this is actually somehow proportional to a kind of divergence you can compute on the distribution. So it's a kind of, not very strong, but a kind of weak divergence. Yeah. Because, since S score model and the original score are representing the distribution, their difference is actually a sort of divergence, right? Still, you have a distribution, you put it inside the definition, you find out the difference between the two distributions, right? So you can think that this SW is modeling one distribution, PW, whose logarithm, and then you take the derivative is SW, that is your model distribution, and then you have the true distribution P, and then if you put it inside the risk term, then this is going to be one other divergence, right? Dummy divergence, but it's something. Questions? No question? Okay, now, given this result, do you think that you can train a score model? Let's do it together. So say I want to train a score model. What I'm going to do, I'm going to first put one neural network, right? That neural network takes d-dimensional input, d-dimensional output, right? Now that I have this, I'm going to go inside my loop for multiple epochs. Every time I'm going to collect a batch of data, right? Data samples. And then for every single sample that I have, I need to compute this divergence, right? So you can compute it by computing the Jacobian and then computing the trace, or you directly compute the divergence from the output, okay? So I'm going to compute this Jacobian. I also compute the absolute value, the norm of the output of my score. This is going to be one sample loss, right? Now I need to backpropagate over my network to compute the gradient with respect to model parameter w. This is different from the gradient with respect to x, right? And then once I have done this, now I have my sample gradient, so I'm going to average them over the samples that I have, and I update my w each time, right? So it's not a hard training, I guess, right? This is something easy to implement. Everybody's cool? Now, that aside, the fact that we can easily implement this, from the computational point of view, do you think this is a kind of normal amount of backpropagations as compared to other things that you know? If you wanted to backpropagate over one simple neural network, usually you have one guy here, right? Okay, well, it's okay. Here I have some. You have one guy here, right? And this guy is going to get your x, which is x1 till xd, right? And then it's going to give you a few outputs, right? Maybe 3 outputs, maybe 100, maybe 1,000, but it's going to be fixed, right? And then you want to just backpropagate. You're going to just backpropagate from every single of them towards these guys, right? Again, this one going backward to these guys and so on, right? Everybody's cool? Now, what about this here? If I want to backpropagate over this divergence, what should I do? Because this divergence, all of these derivatives are with respect to x, right? Now I want to take the derivative with respect to w, right? So it means that I start here. I need to just backpropagate all the way to everybody in this network to get the gradient with respect, a gradient of this guy with respect to model parameter, right? Cool? Great. Now, the next one is the same, right? I need to backpropagate all the way to just... Now, how many backpropagation I need to do here? D, right? Whereas here it was a fixed. A fix is 1, right? 1, D, right? So it's just a scaling. The number of backpropagation that you are doing is a scaling with the dimension of the data you have, right? This is not a cool idea, right? So this is expensive in terms of computation, quadratic, whereas the normal backpropagation is linear, right? And you know that you never want to compute Hessian, right? Same thing here, right? You don't want to compute D times the same backpropagation, right? So the point is that this is a very easy to do. This is efficient to do, actually, if you had computation. You're going to do a very good job. But the issue is that it's computationally complex, right? It's not complex, exponential complex, but this is still a bit more complex as compared to the normal backpropagation, right? So this is why, even though this is theoretically perfect and it's explaining the whole diffusion process, in practice, we are just going one step further, okay, to just reduce this complexity. Everybody's clear? Everybody's getting why this is complex? Yeah? Because you need to do D times backpropagation at the output, right? This is too much, right? Now, but if you could do this, then you're going to have your trained model, and then the sampling is super easy, right? You're going to have this Langevin dynamics. The only thing that you do, instead of that D term, you're going to replace your trained model, right? So nothing changes compared to the Langevin sampling. You basically just put your score term here, and then this is going, after a bit of time, this is going to sample from your distribution. Everybody's cool? Questions? No question? Okay, so if you got no question, that's it for today. One thing here, what we're going to do next. I hope that I gave you this idea that the whole story of the whole story of diffusion model is that you want to mimic the diffusion process, right? Now, we did it here, we were successful, but the problem is computation. Now, the question is that, is there a way that we implicitly mimic the diffusion? And the answer is yes. What we can do it this way. We could say, okay, it's not hard for us to start from the data distribution that we have. Then we design one diffusion that sends us to a Gaussian, right? We can do it. That is easy. We can easily do that, right? What we did here, we didn't do that, right? We started from some random thing and we diffuse till we got to our data distribution, right? No, the point is that if I can go from this data distribution to Gaussian, then can I also learn how I can get back? Yes, you can, right? And this is the trend nowadays, diffusion model, right? So right now here, what you are doing, you are getting back. And to get back, you learn this score function, right? Which is a very sophisticated way to do it, but it's computationally hard. Now, to just somehow bypass this middle score calculation, you're going to just do it implicitly by going first from your own data to a Gaussian thing. And how we can get from this one to this one, there is a very nice result of the same Langevin dynamics, which says when you do know how to go forward, then by some manipulation, you're going to know how you can get backward, right? So we're going to start learn how to go actually backward, and then from that manipulation, we'll learn how to go get back to data, right? Everybody's clear?